shirt on today. For this. Just for this. Just evidence. There we go. Anyway, Dunder Mifflin. If you know who this guy is, beats bears, bees. Anyway, this is not a free body diagram. This is an illustration, okay? An illustration is not a free body diagram. But let's add in some more information to this illustration. I want to say that there's an applied force. I'm not drawing the person this time, but there's something, somebody, something is applying an 18 Newton force to this system. Mass 1 has a mass of 10 kilograms. Mass 2 has a mass of, mass 2, 5 kilograms. And you notice that I'm trying to stick to 3 significant figures for all of these. I'm doing that on purpose to make things easy later, okay? So I'm being thoughtful. Acceleration due to gravity, we're on Earth, 9.81 meters per second squared. And I'm just putting out information. Let's say that for this sliding boxes, we'll have an up, down, right, left reference frame, and we'll make up be positive and right be positive. Sure, why not? Now, before we answer any of these questions down below, I want to write out a list of assumptions. And these assumptions, some of them are going to be assumptions that are going to carry forward for like all of the questions we do. Some of them will be ones that are just specific to this question. One assumption is that this particular system, so this system, is frictionless. We'll deal with things in the future that have friction. For now, though, we're going to say that this particular system is frictionless. This is a two-body system. Now, when I say that something is a two-body system, the fact that there's two bodies means that there are two objects. The fact that it's a system means that these two objects are all kind of working together. They're all a part of the same thing. Okay? They're acting in unison somehow. Notationally, if you see a subscript for cis, cis is going to be short for system. And something about this system is a rigid system. Well, what does that mean? Well, a rigid system can't stretch or compress. And think about what that would mean if this was not a rigid system, one of these two boxes could be made out of sponge and could like collapse if I push on it or something, right? So to say that it's a rigid system conjures to me, like, you know, my basic brain, that conjures up the image of like the wooden blocks that I played with as a kid. You know, they're non-compressible. Sorry? Something solid, yeah. Something solid that can't squish, right? Yeah. All right, and then finally, these objects don't accelerate vertically. And that is a reasonable assumption based on a common situation like two objects sliding along a tabletop, okay? So when I look at these two objects that look like they're sliding along a surface, they're not accelerating up or down because it's a reasonable assumption to say that they wouldn't blast off into space spontaneously or fall through the table, okay? So that's a reasonable assumption. Now the first question is, what's the acceleration of the system? And if I want to have an acceleration for the system, it seems to be sensible that I might want to draw the whole system. So here's the system. I'll call it M cis. That's both boxes whacked together as one, kind of like as one object, because they're going to be together. And cis is short for system. Okay? So when I talk about force due to gravity acting on the system downwards, and I talk about force normal acting on the system, and since this is a frictionless situation, there's no force acting to the left if I look at my illustration, but there is an applied force acting to the right. And whenever I do free body diagrams, I got to have my forces acting outwards from the center of mass. So notice that over here in my illustration, there's a force butting up against 1. But when I talk about the free body diagram, it's acting outwards from the center to the right. Okay? Just like a shift in thinking. Anyway, things that I could think through if I'm trying to figure out the acceleration of the system. F net in the y direction, based on this statement here about don't accelerate vertically, F net y must be equal to 0 newtons. In other words, the F normal for the system and the force due to gravity for the system must be balancing each other out, right? F net y would be 0. F net x, as I look at this, well, this is a pretty simple one. Isn't F net x just F applied? There's nothing else. There's no friction or anything. So F applied. Now, there's going to be people, they say like, oh, we know F net x, we know F net y. I know what to do. F net is equal to F net x squared plus F net y squared, all square rooted. Is there somebody here that could tell me why that might not be a very fruitful avenue to go down? Yeah.
Because F net y is 0, so then 0 squared is just 0. Then F net x squared, whatever you get, you're just going to square root that, so it's just going to be the exact same thing.
Yeah, it turns out that if there's no y component anyway, this is just not like a very helpful thing to do. It's not that it's not true anymore. It's just extra legwork. Why bother, right? So what we could jump to, and I would expect that most people would jump to, is to not write this line. They would say, okay, well, F net for the system, look, this would read, the net force acting on the system is equal to the mass of the system times the acceleration of the system. That's how I would read that statement. The net force acting on the system is equal to the mass of the system times the acceleration of the system. Now the question is, can you find the acceleration of the system? Sure, why not? A cis is equal to F net cis. And if you're wondering where this formula came from, it's just Newton's second law. Okay? F net cis divided by the mass of the system. Now, if I want to be smart about this, I could say, okay, well, F net cis, well, that's actually F applied. And just to make it really clear to see what's going on under the hood, mass of the system really is mass 1 plus mass 2. Right? I could expand that out as the binomial that it is. Don't tell any math friends that we have two equal signs on the same line. They wouldn't like the form. But we plug in our values, 18.0 newtons, divided by 10 kilograms plus 5 kilograms. Basically, it's 18 divided by 15. Somebody who's quick on the calculator, what's the answer? Nice, yeah, nice round 1.2. And actually, it should be 1.20 because we got 3 sig figs, meters per second squared to the right. You know, just because I'm trying to write large so everybody can see my writing, I didn't leave myself enough space for a therefore statement. But of course, we could write a therefore statement. You know, therefore the system accelerates at 1.20 meters per second squared to the right. But then there's this follow-up question. The follow-up question is, what's the net force on each box? And so I think if I'm going to do that, I'm going to kind of do it as like a left column, right column thing, because I have two boxes, right? So for box 1, I'll call this box 1. And I'll partition it in half. Box 2. And again, low-hanging fruit gets picked first. For force due to gravity acting on 1, F normal acting on 1. And we've had some practice with, actually we did this exact same scenario, except there was a person involved earlier. Force normal acting on 2. If I look at the free body diagram for box 2, I'll just draw this vector. What should I call this? What would that one be called? Look at your illustration. That force there, 1 acting on 2. It would be force of 1 acting on 2. I can't say that it's force applied because whoever or whatever is applying that force is not touching 2. You have to actually be touching 2 to be acting on it, unless you're going to be like a Jedi or something, right? And that would be a different force. All right, so force of 1 acting on 2, but if there's a force of 1 acting on 2, there has to be a... Yeah, over here. Force of 2 acting on 1. And while we're talking about object 1, Isn't the applied force attached to object 1?
Yes.
Right? That is true. Force applied. Here. Now, one thing that I haven't told you about free body diagrams yet, and I want to tell you now, I want to let you in on this. One of the reasons we draw free body diagrams is because essentially they're tools for deriving equations. Because this picture right here is equal to F net 1. F net for object 1. That picture is the picture that would let me make an equation for F net 1. Likewise, this picture is the picture that would let me come up with an equation for F net 2. Free body diagrams are useful that way. Okay, and we'll talk about how to do that in just a second. But there's another way to calculate F net 2, because that's what we're asked for, F net 2 and F net 1, and it's using Newton's second law. So simultaneously, F net 1 could be calculated as mass 1 times acceleration 1. And F net 2, I'll give myself a little bit of territory here, F net 2 could be calculated as mass 2 times acceleration 2. And people say, well, we don't know acceleration 2. Oh, but we do. We do. I heard it. Isn't acceleration 1 equal to acceleration 2? They're actually equal because of what I said way back up here. It's that it's a rigid system. A rigid system means everything's moving along together. No squishiness, no stretchiness. All just moving along together like blocks of wood. So acceleration 1 equals acceleration 2, which is equal to the acceleration of the whole system. So we actually found the acceleration of the system already, which means that we know acceleration 1 and acceleration 2. So if I want to find F net 1, I'd say, okay, well, mass 1 is 10 kilograms. Acceleration 1 is 1.20 meters per second squared. We figured that out earlier. 10 times 1.2 is 12. 12.0 newtons. Now it happens to be 12.0 newtons to the right because it's positive. I want to take a look at this guy over here. F net 2, mass 2, 5 kilograms, 5.00 really, but I'm going to run out of space, times 1.20 meters per second squared. 5 times 1.2 is 6. 6.00 newtons to the right. I got the net force on those two individual objects. Well, that's useful, actually, for the next part. The next question asks us, could we please find the action-reaction force between the masses? Can we find force of 2 on 1 and force of 1 on 2? And honestly, we had to do part B so we could even get to part C. This is a very heavily scaffolded question. What I could say is that F net acting on 1, here look, this is me using this picture to come up with an equation. F net acting on 1 is actually force of 2 acting on 1 plus force applied plus force of normal acting on 1 plus force of gravity acting on 1. And let's all agree, doesn't normal and gravity just counterbalance each other? Because we already said that. Those guys are gone. That means that I have an equation where I could say, hey, if I want to know force of 2 acting on 1, because that's the action-reaction force, I could say force of 2 acting on 1 is equal to F net 1 minus force applied. See that? And I can say, okay, well then that means that force of 2 acting on 1 is equal to, well, I already calculated F net 1. It's 12.0 newtons. Even positive 12.0 newtons because it's to the right, minus F applied, which was 18.0 newtons. Look at that, negative 6.0 newtons, or 6.0 newtons to the left. And people say, well, what about that other free body diagram? Well, no problem. Other free body diagram, F net 2 is equal to force of 1 acting on 2 plus force normal acting on 2 plus force of gravity acting on 2. By the same logic as before, normal and gravity actually do balance each other out. So what I could say is that F net 2 is equal to force of 1 acting on 2. And force of 1 acting on 2, well, F net 2 I calculated as being 6 newtons to the right. I just did that back in part B. So 6.00 newtons positive. Or I can say, all right, well, force of 1 acting on 2 is 6.00 newtons to the right. And I think, oh my gosh, 6 newtons to the left, 6 newtons to the right, isn't that equal but opposite? That's Newton's third law. We just proved it. We went through this whole page and we showed that Newton's first law, force of 2 acting on 1 is equal to the negative of force of 1 acting on 2. This problem bears it out, okay? That's a nice like starter level question. Now next time we're going to carry on with the next level of question. And if you're somebody who's absent for the next lesson, you're going to want to make sure that you follow it on the video. You know, there's going to be people that are absent for the next lesson. And don't worry, we're going to take care of you